right, we're going to talk about section 1.4 and 1.5 because they're brief and go together. So section 1.4 is on voltage. So I'm trying this different marker thinking it wouldn't squeak, and it does squeak. So I might as well use the other one that I like. So we'll use this squeaky marker. So voltage is the potential difference between 2 points. Very simple definition of voltage. Potential difference, that's going to run off the screen, is this difference between 2 points. So if I have a point A and a point B, and I want to know what the potential difference between those are, that will give me VAB. So the voltage between A and B. And if I want to look at the voltage from B to A, it's going to be the same value, except negative. So minus VB to A. And voltage is dW dQ, where W is our energy. Q, of course, is our charge. We've seen that before. V is our voltage. So our voltage is our change in energy with respect to charge. So it's 1 volt equal 1 joule per coulomb. Or a joule is a Newton meter. You can say 1 Newton meter per coulomb. Polarity for voltage is very important. So if we have a dummy element, we don't care what it is. Right now it's just a square. And we want to know the voltage across this square. So we would take our probes in the lab, we would put them from A to B, or we would do our calculations if we're talking about theoretical, and we would find our voltage AB. So if I'm putting my positive lead at A, my negative lead at B, then I say there's a voltage drop from A to B. I need to draw polarity. So VAB, voltage drop. If I want to look at VBA, then I'll say there's a voltage rise. So that's just terminology that we'll be using. Again, lowercase, capital case, we typically use a capital V for DC voltage, and we'll use a lowercase v. I usually draw mine like that, just so you can tell it from the capital V for AC voltage. So that's really all that's in 1.4. The potential difference between 2 points is an important concept because you will use that later in circuits and in electronics if you take classes beyond circuits. Section 1.5 is on power and energy. So power is the time rate of expending, oh, I got my knee brace in here, isn't that lovely? Is the time rate of expending or absorbing energy. So time rate of change of absorbing or expending energy. So power is the rate of change of energy with respect to time. Or 1 watt, capital W is our watt, is 1 joule per second. So over here we had joule per coulomb for voltage. Talking about power, it's joule per second. So remember what else we have learned so far. We know that current is dQ dt. We know that voltage is dW dQ. Power is dW dt. So what we end up with is P equals VI. Power equals voltage times current. Very important. P equals VI. P equals VI. P equals VI. We'll use that over and over again, especially in electronics. So if we look at that mathematically, so our power of dW by dt is equal to our voltage, dW dQ, times our current, which is dq dt. That gives us the dw dt. P equals VI. Very, very important. Last important concept is the sign convention in this section. A squiggly line here. So the sign convention, again, we're going to draw some dummy element here. Voltage V across it and current I. This tells me my current is entering my positive terminal. So I say P equals positive VI. Now if I have my current going the other way, so same polarity on my voltage, my current is going this direction, so it's coming around here, then I say P equals minus VI. That's the passive sign convention with a sign convention. We use the same convention when we look at Ohm's law here in a little bit, so it's important to learn this concept now. And we say that a positive power means that the element is absorbing. A negative power, like down here, means that it's supplying. So since power has to be consistent, the power absorbed has to be equal to the power supplied. And again, we will use that, so understand that concept now.